Hello, thank you all for joining us. This is NOAA's Environmental Leadership Seminar Series. And we are happy to welcome Pam Sullivan from NESDIS's Office of Geostationary Earth Orbit Observations. Thank you all for coming. This is a great turnout already. We have 131 people. And I forgot to say, my name is Allison Burrell. I'm a communications technical manager over at the Ocean Service. And again, I'm really happy to welcome Pam Sullivan from NESDIS's GEO to talk to us about NOAA in space. And I will pass it over to you, Pam.
Thanks very much, Allison. Hi, everybody, and happy Halloween. I learned in one of the previous NOAA leadership seminars that the NOAA mission actually dates back to 1807 with the coast surveys that were originally chartered by President Jefferson. Today, we're not going back quite that far, but we are going to go back to at least the Eisenhower administration and the start of the space age. And we'll talk about what NOAA's been doing since then. If we have time after we talk about NOAA satellites, and if people are interested, we can come back and we can talk about this background image that's on here. This is something called the Hubble Deep Field, which is pretty cool in and of itself, but nothing really to do with NOAA. So the topics we will cover today, early weather satellite history. Then we'll talk about the various kinds of satellites that NOAA flies, those in low Earth orbit, geostationary orbit, and then space weather missions that are from different orbits. We'll talk about some of the partners that we have that help us with observing the Earth. We'll talk about why we do this. We'll give you a little peek of what the future of NOAA satellites looks like. And because they asked me to, I'll talk a little bit about my career, and then we'll wrap it up. All right, so going back to the very beginning of the space age started when the Union of Soviet Socialist Republics, the USSR, launched the first artificial satellite called Sputnik 1 that happened on October 4th, 1957. And then the space race was off. You can see the US launched its first satellite 4 months later in January of '58. The value of observing weather from space was really understood from the very beginning. You can see it didn't take very long. It wasn't until, it was just in the next year in 1959 that they put the first experimental weather camera on one of the early satellites called Vanguard 2. That was not actually successful, but they did not give up, and they actually launched the first successful weather satellite called TIROS-1, and that stands for TV Infrared Observational Satellite. That was actually launched by NASA, and that mission lasted 78 days, collected about 19,000 images. You can see one of the images depicted there. Not great compared to today's standards, but the first time really that people were able to observe the extent of clouds and actually see storm systems from space. So this technology pretty quickly proved useful, and basically we've had weather satellites in orbit since then. And all of that actually predates NOAA, which was established in 1970. And part of the reason that NOAA was established, it was recognized how important it was to have an operational weather forecast service backed up by space observations. Let's see, a few years after that, the first geostationary weather satellite called the Synchronous Meteorological Satellite, that was an experimental satellite, that was launched in 1974. And then the very next year, that series turned into what we know as our GOES series satellites. So 1975 was the first US geostationary satellite. And the background image here is a picture of TIROS, that first low Earth orbit. You can see it's round, and the way that it operated is it actually spun on purpose and that was to give it good stability. So spinning actually, like a top, when you spin a top, you can tell it's while it's spinning, it's very stable, and that was important, in order to give the cameras that are there on the bottom a good stable view of the Earth scene that it was looking at. All right, so technology moves pretty fast, and pretty soon other organizations were involved. The U.S. DoD launched its first weather satellite into low Earth orbit in 1962. This was a series called the Defense Meteorological Satellite Program, and it flew those spacecraft for years. In fact, some of our colleagues in our operations center in Suitland, Maryland, are still flying DMSP satellites on behalf of DoD. In the 70s, Japan and Europe both got into the game. They launched their first satellites to geostationary orbit. And then in the 90s, NOAA introduced its first 3-axis stabilized geostationary spacecraft. Before that, all the satellites were spinning, as I mentioned. The 3-axis stabilized is really important technology leap, because although the spinning satellites have really good stability, they can only look at Earth for part of that spin. So if you want to look at Earth all the time, you need to have a 3-axis stabilized spacecraft. And so, again, NOAA introduced that with GOES-8 in 1994. And that, the benefits of being able to stare at the Earth all the time is you can collect more signal. And so, there's light coming up from the Earth all the time, and the longer that you can stare at it, the brighter that signal is. And so that gives us better information about the Earth scene that you're looking at. It also lets us scan faster, so we could collect data at a more rapid clip. So again, a very important technology step. And then in the late 90s, NASA really ushered in what I think of as the modern era of Earth observation. So the background image there is from one of NASA's EOS Earth observation systems satellites. So this is a new camera with very high resolution, multicolor. You can see really how beautiful and the depth of view that you get with that. So this technology made its way from NASA into the NOAA missions, and this is pretty much the era of technology that we're flying on both our low Earth orbit as well as our geostationary orbits. All right, so getting into a little bit of our where we fly them and why we fly them. So low Earth orbit, this is also called polar orbit or sun-synchronous orbit. These are satellites that, as you can tell from the name, are not too high. They're only about 512 miles up. That's close enough to drive to in a day if you could drive straight up. But the orbit that these folks or these satellites are in is designed for global coverage, and you can see in the background you can see the swaths that it makes. As it passes the Earth, it basically gives you a global view of everything that's going on Earth once per day. These satellites, there's a lot of different kind of low Earth orbits, right? You can have a low Earth orbit that goes around the equator, but NOAA has its satellites designed so that they cross the poles. And that's in order to give that global coverage as is depicted here. The NOAA orbits are also chosen to be sun-synchronous. That means every time the satellite crosses the equator, it's happening at the same time of day relative to that local area. So, for example, our current LEO satellites cross at 1 p.m. in the afternoon every time it crosses the equator. So the benefits of LEO, again, that global view, which is really important if you're doing an application that needs that global view, such as numerical weather prediction. And our current generation of LEO satellites are called the Joint Polar Satellite Series, or JPSS. This is a nice graphic of it here. You can see all the little labels are the names of the cameras or the instruments that the JPSS carries. And its two main instruments are a microwave sounder that helps with numerical weather prediction and an infrared sounder that does the same job. The infrared sounder actually has improved spatial resolution, but the microwave sounder is really important because it can see through clouds. But both of these sounders, the job that they do is that they're looking down through the column of atmosphere, and they're looking at very precise, little wedges of the atmosphere, and they're measuring temperature and moisture. So a lot of detail that they get about a column of air, and as they cross the globe, over the course of a day, all of that information is really getting fed to the National Weather Service for their numerical weather prediction. Another job that the LEO satellites do right now is ozone monitoring. That's with the OMS instrument. And it's also got a camera that produces imagery of weather conditions with quality similar to what we were looking at the previous chart. And NOAA 21 is our current operational satellite, although we actually have NOAA 20, and we're actually, NOAA is still using some of the NASA satellites, like the EOS satellites that I mentioned. Those are still up there, still working as well. All right, so geostationary orbit, another important orbit for us. The benefit that you really get from GEO is the satellite orbit is designed at the altitude that it is, which is 22,000 miles above the surface. At that altitude, it is orbiting the Earth once per day at the same rate that the Earth is rotating. And so, because they're both rotating at the same rate, satellites in GEO orbit are always over the same ground point, which is really important if you want to be watching the same point all the time. As you can imagine, for a hurricane that's about to hit Florida, right? You want to be watching that storm all the time. You don't want your satellite to go over the horizon and then come back later. So very important to have these complementary satellites. The ones in LEO, again, have that global coverage. The ones in GEO really designed for severe weather watches and warnings. And our current geosatellites are the GOES-R series. There's a picture of the satellite there. This happens to be at the Lockheed where the satellite was developed. The GOES-R series has two instruments that look at the Earth. That's our main camera, the Advanced Baseline Imager. And then the GOES-R also has a camera that's dedicated to looking at lightning, again, in real time for storm monitoring. And then the GOES-R series also has a space weather observing mission. It's got two instruments. They're looking at the sun directly, looking at solar conditions and solar energy coming from the sun. It's got a couple instruments that are looking at the space environment in the vicinity of the spacecraft. So one instrument is looking at particles, energetic particles that are in the neighborhood, one looking at the magnetic field. And then on GOES-U, only on GOES-U, we also have a coronal mass ejection camera that's looking at the sun and looking for mass that's ejected from the sun. So space weather. Space weather, let me just start with a definition of that, or at least Pam's definition. Living with a star can be really dangerous, which is what our sun is. And so, it's generating energetic particles that are going out into the solar system all the time. They're not at a fixed rate. The sun can be very fickle. It can eject massive amounts of charged gases and charged particles. And some of them, if they come towards Earth, we care about because they affect things like communications, GPS signals. They affect people in high altitude aircraft. They affect astronauts. They affect spacecraft that are orbiting around Earth as well. So we monitor the sun in order to understand those effects that it might have on things that we care about on Earth. There's a lot of different things that are monitored, and there's a lot of different locations that we use to do that monitoring. So the measurements that we're taking right now are images of the sun. Again, radiance from the sun, how much heat is coming off the sun. We do coronal imagery, so that's imaging of the corona or the crown atmosphere around the sun. Energetic particles and magnetic fields are all things that we measure to understand space weather. And I mentioned we do that from geostationary orbit with the GOES satellites. Another good place to do that monitoring is something called the Sun-Earth Lagrange Point 1. That's the L1 point. In the diagram here, you can see it's on the line basically between the Earth and the Sun. And so from that vantage point, you can see everything that the Sun is doing, and you can detect particles in the magnetic field as it comes by the L1 point before it actually gets to the Earth. The Lagrange point 1 is about 1 million miles away from Earth. So again, it gives you a little bit of an early warning. Another good place to observe space weather from is the Lagrange point 5. You can see that at the bottom of the graph. And the thing that you can imagine getting from there is kind of the sideway view. So at L1, you can see things coming directly towards you, but sometimes when things are coming directly towards you, you can't predict exactly, what direction it's going. If you've got that side view from L5, you can get a better view. And really, scientists like to use, instrumentation at all of these locations in order to get the best possible view of space weather that might be affecting the Earth. So our current space weather observation, NOAA is really relying on just its GOES satellites and GEO. Those are the only things that are really doing NOAA measurements right now. But we have a lot of partners at NASA, at the European Space Agency, and others that are collecting measurements at L1 that help us with the space weather forecasting that we're doing. NOAA is working very hard right now on building its first dedicated space weather mission called the Space Weather Follow-On, and that is actually planned to launch next year. So this chart kind of summarizes all the satellites that NOAA is really operating now. NOAA operates 18 different satellites. You can see, obviously, the Earth in the middle there. The red represents the LEO satellites. The blue ring represents the GEO satellites. And you can see there's like more than one of each satellite in each of these locations. And then you can also see out depicted towards the sun, the Discover mission that we're operating as well, even though that's a NASA spacecraft. But we're getting data from all of these satellites to do the forecasting that we do. So this seems pretty impressive, right? And on the next chart, I'm going to show you who else is doing all of these observations. So this chart adds in the satellites that we are partners with, that we're getting data from. So satellites that are built by Europe, whether that's the European Space Agency, the European Meteorological Organization. It adds in satellites that are built by Japan and Korea, Taiwan. I think there's an Indian satellite in there. There's satellites from Canada in there as well. And so you can really see that even though we get a whole lot of data from our satellites, there's a whole lot more satellites out there that other nations are doing. And one of the really good things about weather observations is that these are understood to be data that ought to be shared, and they are being shared because it's a public good that we want, not just the U.S. to benefit from, not just the country that built the satellite to benefit from, but a public good that we want really the entire inhabitants of the world to take advantage of. So anyway, so the partnerships are really important for us to share our data and to get the data from other folks. And one reason, of course, to do that is that the weather doesn't know anything about national boundaries, right? In the U.S., most of our weather travels across the Pacific into our weather space. And so it's important to have these satellites in Asia and be able to see storms or weather patterns, and sometimes even like volcanic eruptions coming that direction towards us. It's important not only for the forecasting that we do in the States, but also for air traffic and ship traffic that crosses the ocean. And then from the other direction, the hurricanes that affect the U.S. most often start off the coast of Africa. And so it's important to have the view there to be able to watch the storms come our way. So again, really good story about the partnership that we have with agencies around the globe. And so here's just an example of partnerships at work. This is actually a composite image. It's showing the image from the Japanese satellite on the left side, the US, the GOES satellites in the middle, and the European EUMETSAT satellites on the right. So all stitched together, but you can see, that you get a really global view. And again, that is the purpose of the data sharing that we do. Okay, so why do satellite observations? I didn't know until about 5 years ago that there's actually a law that says we have to do this. Something called 15 U.S. Code 313. The Secretary of Commerce shall have the charge of forecasting of weather, the issue of storm warnings. There's another one, Code 1532. So the Secretary of Commerce is authorized to prepare and issue predictions of electromagnetic wave propagation conditions and warnings of disturbances in such conditions. If you don't understand it in the legal language, that last one is about space weather. And then there's also something called the Primary Mission Essential Functions of Government. DOC has been assigned a couple of these. One of them is to provide satellite imagery. And so we do, as directed, collect and provide the nation with critical intelligence data, imagery, other essential information for predictive environmental and atmospheric modeling systems. So, like I said, that was interesting. But of course, it's a law for a reason. Congress understands, I think most people understand, the benefits, and it's really all about lives and livelihoods. We do weather forecasting. There's a World Meteorological Organization has done studies that they estimate the economic benefit of weather forecasting to be $162 billion a year. And 95% of the data used in forecast models comes from satellites. So obviously very important to have the satellites feeding this process. And of course, these storms are very deadly. Last year, the Weather Service tallied over 700 fatalities due to weather. In this year, the NOAA keeps track of the billion-dollar disasters, and there's been 24 disasters thus far in the year that have totaled more than $1 billion each. And of course, climate change is another benefit that we get. These satellites, again, dating back to 1960, and they've really been watching the planet, and a lot of the observations that the satellites make are recording what they call key climate variables. So we are looking at the temperature of the atmosphere. Our satellites are looking at cloud cover. A warmer planet has more clouds. We're trending that. A warmer planet has more lightning. Now that we have a lightning mapper, we're looking at that. Warmer planets have more precipitation. Again, that's a metric that we can track using the satellites. So anyway, so critical for all of those reasons. All right, a little view of what is coming. We are actively working right now on future satellites in all of these domains, space weather, LEO, and GEO. One of the first things that we will see is actually going to happen next year, which is we're going to start this coronal mass ejection monitoring. There's a camera, the new camera on GOES 19, will be doing this function operationally next year. And then the SWIFO satellite that I mentioned, that'll be launched in 2025 as well. It's got a camera that will do the same job, but it will be at that L1 point where it gets kind of that closer view of the sun. On the LEO front, they are working hard on a satellite called QuickSounder, and it is really going to be a prototype of what their next generation LEO space architecture is going to look like. It will be carrying a microwave sounder, and so it will add to the capability of microwave sounding that we're doing now, as well as paving the way for what's to come in the future LEO architecture. And then a few years past that, out in 2032, we are planning the next GEO capabilities. The system is called GeoXO, and that first launch in 32 will be carrying an imager and a lightning mapper, continuing what we do now, as well as adding an ocean color sensor. So a sensor that'll be looking at the coastal areas around the U.S., the exclusive economic zones around the U.S. A few years after that, another GeoXO spacecraft will launch, carrying new capabilities. We're actually adding an infrared sounder to our GEO complement, as well as a sensor that measures atmospheric composition, which you can think of as air quality. That's really its job. It'll be doing hourly scans of air quality across the U.S. And so, so some big steps planned in the near and a little bit further on future. Okay, this is the least interesting chart in here to me, but the seminar organizers thought it might be helpful for folks to hear how my career went in, so that folks can think about if they want to follow a path and get into the NOAA space business as well. So I have a engineering degree, bachelor's, and the Air Force paid for tuition. I was ROTC, which was really nice of them. But then I owed them 5 years. So I was in the Air Force for the first part of my career. My first job was actually being a flight controller for the Space Shuttle. I was stationed down in Houston, learning how to do things to make the shuttle operational. And I also worked on some payload experiments that would fly on the shuttle as well. So that's a picture of me sitting in a simulator of the Space Shuttle in Houston. After I got out of the Air Force, my first job was with NASA. I came to work at NASA Goddard Space Flight Center. I was the instrument manager for actually the imager that was on the GOES-I series of spacecraft. Did that for about 6 years. That was a contract value worth about $150 million. I put the dollar value on here. It's certainly not the only measure of a career. But if you're on sort of a project management track, like my career has been, it's a good metric, because you can see your average management track proceeds from managing small things to managing bigger things to managing bigger things. And so kind of mostly followed that track over my career. So again, I was working on the GOES-I 3M satellites, but I was a NASA employee. And I should have mentioned, all of the NOAA satellite programs are jointly managed with NASA. It's been a partnership that has, again, gone back to the very beginning of weather satellites, where NOAA relies on the expertise that NASA has for developing complex things like spacecraft and instruments. So anyway, so I was part of the NASA half of that partnership on GOES-I through M. But I left that project. I went to work for the Hubble project. I was an instrument manager again on a camera that went up on Hubble. After that job, I moved to the James Webb Space Telescope. I was the manager for all of the payloads. There were 4 different cameras on James Webb, and I managed those. From there, I moved to become the deputy project manager on something called MMS. That's actually a heliophysics mission that was actually built in-house, as they say, at Goddard. I was only there a short period of time before the program called NPOS, which was the precursor to JPSS. They were running into some trouble with one of their instruments, the VIIRS instruments, and they needed someone to kind of go out into the plant and help get that instrument delivered. So I did that for about a year. And from there, again, the NPOS turned into JPSS. So I went to work for JPSS as the deputy flight project manager there. And then I got the opportunity to become a project manager on the GOES-R series, still a NASA employee at this time. But I did that for 6 years until when the NOAA program director job opened up for GOES-R. I applied for that, was doing that. I'm still doing that, actually. Although NESDIS reorganized last year, and so I got a new title, Director of GEO Observations, and so I'm currently managing GOES-R as well as the future GEO sensors called GeoXO. So anyway, so like I said, that's a career path for one person, the only thing I will say, this is an easy chart to draw in retrospective. If you had asked me while I was in any one of these boxes what my plans were going forward, most of the time I wouldn't have had a good answer for you. So I guess my message is it's possible to have a really great career even if you don't have a clear idea of where you want to end up. So just enjoy the job that you're doing right now. Look for that next opportunity, and most of the time, I think that leads to a good career. All right. So in summary, NOAA's been doing satellite observations really since the dawn of the space age. Our satellites observe from many locations. They work in conjunction with partners to monitor and predict conditions that affect us on Earth. The future missions are only getting better in order to meet emerging needs that our users have, and it is something that you can be part of if you like. So with that, I think I turn it back to Allison for questions.
Thank you. Thank you so much, Pam. Okay, so yes, let's dive into questions. We've got some good ones. I wanted to start with, sorry, there's a little bit of feedback. Are you hearing that, or is it just me?
I hear it very low. It's not distracting for me.
Okay. So referring to the slide with all of our satellites and the partner satellites, it looks very busy. And we got a question that I've definitely heard before is, it looks really crowded up there. Do these satellites ever get in each other's way? And also, if it is crowded up there, how do we mitigate that?
Yes and no. There certainly are a lot of satellites up there. I forget the current number. Thousands of things are orbiting space. Space is still pretty big. Most of the time, even if they're close, they're still miles apart. There is, but people do track this. There is an organization that is looking at everything that is in Earth orbit and tracking it very precisely, to the point where if you've got a satellite, you might get a call that says this other satellite, or sometimes it's a piece of space junk, is coming your way, and it, and they give you the opportunity. Do you want to do something to get out of its way, or to to change your maybe shut something down that you're worried about being damaged? So that traffic cop function is a very active role, and in fact, it's one that NOAA is taking on in the Office of Space Commerce. So
that's great. There was a question, actually. I'm hopping around. How does NOAA satellites work with the Office of Space Commerce at NOAA?
Yeah, I think again they're trying to set up the systems that will be able to do this forecasting. and be able to track where everything is, and be able to send out information. So we would be, I guess, customers of theirs. You know, they would have a system that would send us reports that something is coming our way, and we need to do something about it.
That's awesome. Another partnership, big partnership with NASA. So how does NOAA and NASA work together? How do they work together on satellite launches? Who has what role in the technological development, the launching, the funding? I can see that being hard. I mean, it's hard to work within an agency, let alone across agencies on such large projects.
Yeah, luckily we've been doing it for a while, and you know, the roles, you know, sometimes they've been, you know, conflicting, confusing, but we've kind of gotten into a pattern where we've done it enough that, and we try to do it the same from project to project. And so generally what we set up, you know, NOAA advocates for the funding. You know, NOAA's like, I've got this mission, I need to make this observation. They could go to Congress, they justify the budget. The NOAA will have the overall program management responsibility generally. NOAA will typically be the science lead because we're the ones, again, that are trying to meet a need for our customers. NOAA will be the overall management for like the budget. But we turn to NASA really for the hardware pieces of it. So for the satellite, for the instruments, for the launch service, we go to NASA and we say, you know, we need this capability. Would you develop the system for us? And so generally NASA is leading what we call our flight project. And then NOAA funds them for the work that they do on our behalf. On our ground project side, that is typically led by NOAA, again, because the ground systems interface with our users. It interfaces with, you know, common services that we have as well, and the rest of NOAA. You know, we're the best position to know how to get data to the Weather Service, et cetera. So, so our ground projects are typically led by a NOAA employee. I will say on both our ground project and our flight project, there are NOAA and NASA people in both. And so we've got like deputy project managers are, you know, of the other agency. Occasionally we've had observatory managers that are NOAA, instrument managers that are NOAA. We've have, you know, ground systems has had systems engineers that are NASA. So it's, you know, we kind of give the lead responsibility to the agency with the most expertise, but we work it jointly together at a lot of different ways. And in fact, the management structure above the program is also a joint NOAA-NASA. So when we go to like a monthly status review or a key decision point milestone, that is also a NOAA-NASA board with the ultimate approval being by NOAA. So like I said, we've done it this way for a while now and kind of worked out the kinks of, for the most part.
So you had also mentioned the Discover mission. That's another joint NOAA-NASA satellite. And someone asked, is there a plan to replace that mission? And I added, you know, or is there anything up there already that's imaging something similar? I'm just curious about that.
So I'm not a space weather expert, but I believe the space weather function that Discover does is going to be done by the SWIFO spacecraft that we're launching, because that's where Discover is right now. It's at that Lagrange point 1, and that's where SWIFO is going. I know Discover has an Earth camera as well, but I don't think anyone's planning to replicate that capability in the future that I've heard of.
And I think SWIFO is launching in 26.
Last I heard, it was 25.
Okay.
They're flying with a partner mission. It's a joint launch, and so they're a little bit at the mercy of their partner. But last I heard, it was kind of the latter half of 25.
That's even better. Okay. When you were going through the history of satellites starting in the 60s and on up, there seemed to be a gap between the 70s and the 90s. I'm sure there was lots going on, and they were just wondering why there was a gap or what was going on during that time.
Yeah, I could show you a chart that has like a little bar for every satellite that was launched, and there were weather satellites that entire time, both in LEO and in GEO. So it's just the milestones that I picked out happen to be kind of the first of a thing or a major upgrade, but um, we've had a constant presence of weather satellites really since the 60s.
Right. And so you said when we made that jump in the list that you had, it was 1994 when you had mentioned um,
Those
the
are three axis
three-axis
stabilized. Yeah.
stabilized that goes 8. So, but we did have a question related to that. Do the modern satellites use gyroscopes to stabilize their cameras as opposed to spinning the whole satellite?
Yeah, basically yes. We call them reaction wheels, but they're large weights inside the spacecraft that spin. There's generally 6 of them, and they're at different angles. And so if you spin this one fast and this one, it'll make the satellite go the direction you want. So with um, we have 6, but I think we only operate 4. Someone will probably tell me I'm wrong, but there's some redundancy. But with 4 wheels, you can basically control the speed of them and get kind of like any motion that you want to go in. So yeah, the spinning part is inside the spacecraft in order to make the view that the cameras have stable.
Could you describe the process for planning and acquiring new satellites, like the major steps about design and development? It's a big
Yeah,
question.
it is a big question. And it's actually, I don't, maybe it'll make you feel better. It's actually, we follow NASA processes. They actually have standards, a NASA procedural process that says, here's what you do at the start in what they call phase A. You decide what you want to do. You decide how you're going to do the acquisition. Are you going to build it? Are you going to buy it? Are you going to structure the instruments as part of the spacecraft? Are you going to have the launch vehicle acquisition with so in phase A, you kind of define what you want to do. In phase B, so there's 5 phases in the NASA life cycle. So first, deciding what you want to do. The second step is planning it. How are you going to go about it? Write down, the things we were just talking about, like who's in charge of what. Write all that down. Um, and then in phase C is the start of what they call implementation. So you start building things, you start designing. Okay, I said I need this camera. I've done the acquisition. I've competed it. Industry partner has been selected. Either that or maybe Goddard is going to build the instrument themselves. But either way, in phase C, you start building things. So people do drawings. Here's what I want the mirrors to look like. Here's what the electronics need to look like. You go out and you start buying things. You start buying, the glass for the mirror, the resistors and the capacitors and the everything else that goes into it. So that starts in phase C. Phase D, you've generally got each thing together. You've got an instrument, you've got your spacecraft. In phase D, you're putting these things together. So it's the integration of everything that makes up your system and the testing and putting it through the things that go in space. You want to put through environments that look like space. So you do vacuum testing, you do thermal testing, you do what's called vibration testing, which simulates what the launch is going to look like. And so you make sure that your satellite is going to survive all those environments in phase D. And then in the final step is the launch, and then phase E is the operational phase. And again, all of these are kind of laid out within the NASA structure, and it gives you a pretty good idea of what you should be doing at each of these times, whether it's from a business perspective or a systems engineering perspective, a management perspective. And again, it's one of the reasons we partner with NASA is that they've got expertise in going through that.
And timing wise, from A to E, it can take a decade or more. That's the clincher?
Yes, it depends on the scale of the thing that you're building. On GOES-R, the first planning, and I should say the very first step is generally somebody saying you need money. So for on GOES-R, that started in 1999. We launched the first satellite in the series in 2016, so that took 17 years. And then the phase E for the GOES series goes into the late 2030s. So, the life cycle is really from 99 to 2036 or something like that.
Wow.
So, but GOES-R is a very big, and there's multiple launches, so that extends it. Something smaller like SWIFO, I won't get it exactly right, but I think they went from we need money to launch in about 5 years. So it's a smaller, on a faster scale. But 5 years is probably about as fast as you can go if you're starting from scratch. I will say the Quick Sounder mission that I mentioned, they are trying to demonstrate, can you do that? They'll kill me if I get this wrong, but I think it's like, can you do that in 2 years? It might be 3 years, but they're starting with kind of a defined instrument. They're trying to test the case of, I've got an instrument on a shelf. How fast can I get a spacecraft and launch it? So they're trying to see how short they can make that, because they think that will be important for their future architecture and the ability to be resilient and adaptive, to put up new things quickly when there's a need for them.
And a quick question about Quick Sounder. Will it provide real-time observations?
Yes, yeah, definitely. They're planning to use the microwave observations, just like the microwave observations from the JPSS series.
Okay, here we have one. Do NOAA satellites do any work with mapping, cartography, and charting?
I think the right answer is no to that, although they're certainly used in conjunction with that. I have pulled up a Google map, and I've seen GOES-based fire data mapped on top of that. So there's definitely a role in putting weather data, or in this case, fire data, on top of mapped projects. But in terms of like cartography, I don't think we're generally at the resolution for the satellites that do that.
I like this question. What technology would you like to see on a satellite that we don't have yet? Is there any dreams that you have of future satellite?
Oh, I'm the one that builds things. It's the scientists that have dreams of things. And I saw another question about microwave sounding. That's something that the scientists. It was something we looked at for GeoXO, because the scientists really wanted that. But it's that technology to do it in microwave, because you're really listening to radio waves. In geo, you need a really, really big dish. It would be the only instrument on the spacecraft. You couldn't have an imager or ocean color, and so that makes it expensive if you're just flying one instrument on one really big spacecraft. So from a cost benefit perspective, that didn't make the cut. Another one that would be really cool, that we're actually working with Canada, hoping that they're going to get funding from their government to pursue, is a pair of satellites that would go in something called highly elliptical orbit. This is an orbit that is designed. You might heard it called a Molniya. It's one where it flies close to the Earth on one side, and then it flies far from the Earth on the other side. And what that does is it gives it like hang time, so that it can be looking at the Arctic for a very long period of time, gives you pseudo geostationary coverage of the Arctic regions, which of course is important to Canada. So that, I think, would be a real cool capability, and particularly with more shipping lanes opening up now that there's less ice in the Arctic area. So we're hopeful. that together with Canada, we can collectively find the resources to make that happen.
So in addition to working with partner agencies from other countries and other agencies within the US government, do you work with private industry as well in the satellite production?
Absolutely. Private industry is they're the ones that turn the screws. Basically, I mentioned Lockheed Martin built the GOES-R satellites. We had instruments that were developed by L3 Harris, a company called Advanced Technology Corporation in Massachusetts. The University of Colorado built one. Lockheed actually built two of the instruments. I'm forgetting somebody. The magnetometer actually for GOES was built by Goddard, but the main development and our ground system was built by L3 Harris. So again, most of the work that is actually accomplished ends up getting done by industry, and that's true for the LEO spacecraft and the space weather as well.
At the end of the satellite's usefulness, at the end of its life, what happens? Does it just stay up there? Does it come back to Earth? Does it go out into space? Like what happens to it?
Yep, good question. Depends where the satellite is. If it's in low Earth orbit, which we discussed was close to Earth, typically the last thing it does is it fires its thrusters in a maneuver that is basically pointing it down. So it will deorbit itself, and we aim to have it deorbit somewhere over an ocean, a non-populated area. So the low Earth orbit ones we take out of orbit by bringing them back to Earth, crashing in the ocean. In geostationary orbit, it is actually too far for them to come back to Earth. So we push them into something that's, believe it or not, called a graveyard orbit. So we want to move it out of the geo ring, right? The geo ring is at a specific height, that 22,000 mile height. And so we want to preserve that ring for active geostationary satellites, things that are doing a job there. So the graveyard orbit is actually 300 miles higher. So the last thing we'll do with a geostationary satellite is we'll maneuver to push it up out of orbit where it's not going to run into any of the active satellites. And then we turn everything off on it. And for the satellites at L1, I can't believe they come back. So there's got to be equivalent of a graveyard orbit for the L1 satellites.
I'm seeing a lot of questions about, sorry, I'm jumping around from the end of their lives to the beginning of their launch. What kind of rockets are being used, and how has that changed over time?
Yeah, the rocket industry is very dynamic right now. The 4 GOES-R satellites were launched on Atlas rockets, which have been around since the 70s. The JPSS, the first JPSS, I think, was launched on a Delta, which has been around since the 70s. But basically, we compete the rocket services. So roughly 2 to 3 years before we're launching, we will actually put out a request for proposal. And so we go to whatever industry is active at the time. Lately, that has been SpaceX. They have been either with their Falcon 9 or their Falcon Heavy. They have been the top competitor for the most recent procurements that we've put out. And for GeoXO, which is at least 8 years in the future, we're thinking the Blue Origin rockets are probably going to be candidates. And I wish I could remember the LEO. They just awarded their launch to one of these newer startup companies that I don't think they've had a success. I don't think the company has done a successful launch yet, but their launch is 2 years away. So the company has a plan to do some launches before then, but they're getting in on one of these new startups. And there's quite a few. I can't even quantify it, but there's 5 or 10 that are working on launch capabilities for very small satellites. They wouldn't be They wouldn't be like a GeoXO or GOES-R class, but for the future LEO and maybe the future space weather, because those satellites are smaller, they may be candidates for some of these smaller startup. It's great to see the competition in the industry. For years and years and years, it was just Atlas and Delta back and forth. So a lot of innovation in that part of our industry right now.
I know we do launch these large satellites that have lots of different sensors on them that do a lot of stuff, but is there a benefit to that versus a bunch of these small sats that might do similar work and get launched, like that launch window would, or launch from the initial idea to launch would be shorter if you had a bunch of different things on small satellites instead of all of the things on one large satellite?
Yes, and that's what our LEO team is exploring, that kind of different model, if you will. They're really looking for not, they're not tiny. They're not like the shoebox size satellites that you hear about, CubeSats and things like that. To do the measurements that we want, um, the aperture of the instrument needs to be of a certain size to get enough light in to make that high quality measurements. So so we're not at that smaller range. We're maybe at the size of we're refrigerator sized satellites, something like that. But that's what the LEO team is exploring. Can you develop those faster, and does that make more sense to do kind of a launch on demand? I've got a store of instruments that are ready to go whenever we need them. So again, that's a different business model that they're exploring. It doesn't make so much sense for geostationary because the orbit is so far away. It's really expensive to get there. It makes more sense still for GEO to put, if you're going there, to take everything that you can with you. But for LEO, again, with the advances in the launch vehicle market, with the advances in small satellite technology, it may make sense for them, and that's what they are looking at.
All right, I have one last question. We've talked about so many awesome details about NOAA satellites and the partnerships, but the future of NOAA and NASA are our students currently. And so I'm just curious if you know or want to talk a little bit about educational opportunities for students that are really interested in space and want to work in space technology.
Oh, I'm probably not the best one to rattle them off. There's all kinds of intern programs NOAA has, NASA has, and I would say don't even limit yourself just to what NOAA and NASA has, but look at the companies that are in space. The Lockheeds, the Harrises, the SpaceXs. They all have similar programs as well. So it's our project. We have 10 to 20 interns, summer or longer term that come with us. So there's definitely opportunities, and I'm sure a search will find those very easily.
Yeah, definitely NOAA has a lot of opportunities for students. You just go onto the education section. There's so many summer internships for high school students, college students, graduate students. Yeah.
We do a lot of outreach to grade schools as well. If you go on the NOAA site, if you go on the GOES-R site, there's a section there where if you're a teacher, you can order some study materials, coloring books, any kind of thing like that might be of interest.
Thank you so much, Pam. We also got a lot of notes in here that you can read through, thanking you. They're so impressed by your career path and everything that you've done and are doing. And thank you so much for talking to us. This is being recorded, and hopefully we will have it up online shortly. But thank you so much, and thanks everybody on the NELS team as well. Thank you, Pam.
Thank you all.